Our second presenter this morning is Kevin Bauer. Kevin is a member of NASA's Launch Services Program at the Kennedy Space Center. He participated as part of the Pathways internship program before receiving his master's degree in thermofluids from the University of Central Florida. During his time as an intern, he was involved in developing the thermal desktop model for a CubeSat mission, which will be the topic of his presentation today. Kevin, welcome.
Thank you very much for the introduction, and good morning, everybody. Thank you for tuning in. I wanted to start off by just mentioning that this work is in relation to one of the earlier presentations we had in the conference by Jared Wilhite, and his topic was on the solar white thermal coating. So this is kind of a review of the thermal desktop model related to that work. So just to go over, this is the Passive Thermal Coating Observatory operating in low Earth orbit, or PACCOOL for short. This is a CubeSat project or science mission, and we'll start off by giving you guys a little bit of a background or motivation into how this work got started, and you know, the need for this analysis, a little bit of the mission objectives, what sort of goals we had in mind that determined some of the important decisions, a little bit of the thermal design, and then moving into the modeling approach and the thermal desktop model itself with some temperature results at the end. So in accordance with the space policy directives that we have in place, and you know, the movement into going back to the moon and Mars, there's a need for better thermal control coatings. And in the past, there's been sort of an idealized form or concept of a thermal control coating designed for one astronomical unit away from the sun and far enough away from infrared sources such as planets that could potentially reach to cryogenic levels and better. And this was first suggested by Hibbert in 1961. But since then, there's been no real coating that's reached those idealized temperatures, and so far the state of the art just includes white paints and second surface mirrors, which for the white paints, you typically see something around an absorptivity of 9% and an emissivity of around 90%. And for the second surface mirrors, you see something around absorptivity of 9% and emissivity of 91%. The idea that kind of started with Dr. Robert Youngquist at Kennedy Space Center, he started developing a new thermal control coating that was kind of a compressed powder or scattering particles of a certain material termed yttrium oxide. And he started to kind of do some lab work, trying to test this new coating out and seeing what sort of temperatures we can reach. And so this analysis kind of propped up to get an idea of how this coating would react in a deep space environment. And this could eventually lead to enabling technology advancements for cryogenic fluid storage, or you know, superconductors enabling energy storage, all of which is pertinent for creating habitats on Moon or Mars for long-term space travel. So going into some of the mission objectives that were important to us to keep in mind, starting off with number one, the PACCOOL CubeSat, 3U CubeSat, will be essentially a performance test for this new thermal control coating that was developed at Kennedy Space Center, and trying to compare that to the state of the art, in which we're using AZ93 white paint as the benchmark. And so we tried to incorporate some redundancies in that to try and mitigate any uncertainties that we may have from the results. Secondly, we want to kind of see what sort of temperatures we get. The idea of the coating is to reach cryogenic temperatures, but this coating was also designed for, like I said before, one astronomical unit away from the sun and far enough away from any planetary IR sources. You'll see later on that this CubeSat will be orbiting in a low Earth orbit, similar to the International Space Station. And so since we already know that we are going to have some IR sources, we try and mitigate those by orientation of the CubeSat or any thermal design that we could apply to the housing itself where the samples are kept, to kind of just minimize any environmental sources and just focus on solar radiation solely. The main idea there, even though we may not reach cryogenic temperatures, we want to emphasize a significant temperature delta between these two coatings. And finally, once we have the CubeSat in orbit, the idea would be to use the empirical data to improve the model fidelity from Thermal Desktop, and sort of kind of backtrack or validate what optical properties we're assuming and using in the Thermal Desktop for this new coating. And so going into the thermal design, we start off where the samples are kept and the samples themselves. Like I mentioned before, we wanted to incorporate some redundancies, and so we added, we have 4 samples in total, 2 of which are coated with the thermal control coating developed at Kennedy Space Center, and 2 of which are coated with the AZ93 white paint. Each one has its own temperature sensor, and we have all of them on aluminum samples, and the coating goes on top of that. And the idea behind that was to try and kind of have a uniform internal reaction to the solar radiation, and try and minimize any questions that we may have in the future, to solely just, this is the impact due to the coating itself and not anything else. And so that was the mind, or the thought process behind that. The sample housing itself, like I said, we will be in a low Earth orbit, so we wanted to kind of protect it as much as we can from any IR sources. So we painted some of the outer walls of the housing where the samples are with some AZ93 white paint. We have the interior walls surrounding the samples themselves with a reflective coating, silver plating, and the housing cover that goes on top as well has the reflective coating on the bottom and AZ93 on top. And the samples themselves will be suspended within the sample housing in order to reduce or try and decouple the samples from the CubeSat thermally. There was a decent amount of thought process going into this design, and so even the Kevlar string diameter was considered in order to reduce the amount of conduction, the Kevlar routing as well to reduce the length, any sort of edge that we could get, we definitely try to take advantage of. The CubeSat will be pointing away from the Earth, zenith pointing towards the sun. The sample housing cover, the openings on that cover itself have a diameter that was picked in order to not have any radiation coming into the housing itself and bouncing around, or try and minimize that impact, as well as, avoiding hitting the Kevlar strings with the solar radiation. We wanted it to kind of serve as an aperture, focusing the solar radiation directly onto the samples. If you can see my mouse, there's also separations here from the bottom portion of where the avionics would be. This first separation kind of serves as a barrier from any heat that might be dissipated from the avionics, as well as a spreader conductively spreading the energy into the CubeSat so that it could radiate out and not go up into the sample housing. The The second portion, which we term as the housing adapter, is made out of an Ultim 1000 plastic material in order to try and reduce any sort of conduction up into the housing again. And so those are just some of the thermal design approaches that we took. This is a little bit more of a detailed look at it. This is the full 3U CubeSat, and we're looking specifically at the sample housing. This is just kind of giving you an idea or a better idea of how everything comes together. These are the Kevlar strings that I was mentioning before. We added some MLI in between the sample housing and the outer CubeSat wall. Like I said before, the outer CubeSat wall was coated with AZ93, and this is the Ultim plastic portion adapter and the avionics thermal barrier. To the left, you can kind of see how much care was taken into, we are concerned with the aperture of the housing cover and getting any sort of angles or view factors from the solar radiation. And so we're trying to align the samples directly centered over these openings. And this is an example of how the Kevlar strings were routed. You can see that the samples are kind of two halves, creating one whole. The idea behind that was previous concepts of how we would route the Kevlar kind of gave way to it being in sight of the opening, and so we kind of just wanted to hide those a little bit more. But that's just an idea to give you, or just to give you an idea of how everything kind of came together. So going into the thermal desktop model itself, as mentioned before, the International Space Station parameters were used for the orbits of the CubeSat. The conditions for solar albedo and IR planet shine for worst case hot, colds, as well as my nominal were all taken from the references below. And this is just trying to give you a concept of how much fidelity went into the samples, expecting some temperature gradients, even though most of this is all aluminum. Keep in mind this was work during my internship, and so this is actually my first thermal desktop model that I worked on. I will note that one of the lessons learned was kind of the amount of fidelity needed for certain parts could be changed. In this case, I used Space Claim to pull in some of the more complicated portions and kind of did an auto mesh. Whereas in other portions, you'll notice, for example, like in the samples themselves, I didn't do an auto mesh. I kind of picked those based off, what would be of interest to us. A little bit on the avionics. The thermal desktop model for the avionics was simplified from the actual stack. And so what the approach was to do a single node representation for each one of these with a heat load imposed on that. And on the left, you can see the wattage that each one is outputting. And so I just did a simple box approach, kind of tied all the faces to each one of these nodes and had that as representative heat load from the avionics within my model. And so this is the full CubeSat and thermal desktop, as well as the ISS orbit in which it's orbiting. Just to give you an idea of how everything came together and the fidelity of the model itself. So these are the temperature results that we got. So for the nominal case, we were seeing the thermal controlled coating that was developed at Kennedy Space Center, kind of reaching around 180, 179. So that's the bottom portion right here in blue. The AZ93 white paint, which was used as comparison, is the orange one for the nominal case, sitting around 210. And just for reference, I added the sample housing temperature. And something that did catch my eye was the sample housing was following pretty closely to the white paint, and that's something that I will look into in the future. As of right now, my guess is, the samples, like I said before, are all aluminum, and in this case, the outer wall of the sample housing is coated with the white paint, and so is the white paint sample. But this is just an overview of the nominal case, and below you can see worst case hot and worst case cold numbers, as well as the difference in temperature that you would see. So again, we're not reaching cryogenic temperatures, but we are seeing a significant difference within temperature, and that's a very good sign for the potential of this thermal control coating. And so for some of the future work that I want to be doing with this model is post-processing, including some subroutines that would help me kind of get an overall energy balance on the samples themselves. Some of these subroutines include Q-flow or node map or heat map that are kind of part of Thermal Desktop. And adding those subroutines in the background kind of enable you to get a better idea of what's going on. And so the energy balance would somewhat include like how much energy is coming in from the Kevlar strings, how much energy is coming in directly just from solar radiation, how much energy is coming from the housing cover or sample housing itself, that sort of idea, just to get a better, more confidence with the model itself. And then once we have the CubeSat in orbit, which is due to be launched in sometime in the next 2 or 3 years, we'll have some actual data to kind of validate the model itself. So far, we've only really had some lab testing done at KSC as well as at Glenn, in which we kind of leaned on to kind of bound the temperatures. So we kind of got an idea of what would be the best case scenario, because these lab testing only include solar radiation and not the IR portion. And so we kind of just wanted to get some bounding cases to see whether or not this model is within, ballpark range of what we would expect. But that's pretty much it for my presentation. Thank you for your time and this opportunity, and I hope that you guys enjoy the presentation. If you have any questions, I'm open to them.
All right, thank you, Kevin. Thank you for your presentation. And let's see, our co-moderator is having some technical difficulties, so we split up duties here. Let me fill in here and check out the chat for some questions. And here we go. Let's see. Okay. All right, for our first question, if I can get the chat to cooperate. Here we go. One question. We have an advanced new composite that can be used for prevention of HPV debris, thermal protect, and secondary radiation at the same time. I'm not sure. Maybe the person who, HV, okay, they correction. They meant HVI, hypervelocity impacts. So I think their question is about composites to prevent hypervelocity impacts and do thermal protection and secondary radiation at the same time. Do you have any insight into materials like that?
I do not. That is definitely outside my wheelhouse.
Okay.
But I can look into that and potentially get back to the question.
Yes, maybe if the person who asked that wants to maybe offer a slightly different version or reach out to you via email, maybe you guys could have a little more of a conversation about that. Another question. How will the CubeSat maintain the zenith attitude? Are there reaction wheels and or magnetorques?
There are magnetorques. I didn't go too much into detail with the CubeSat. It was kind of intended to be more of a thermal desktop model review, but there are magnetorques on the CubeSat helping it align towards the zenith pointing.
Okay. Let's see. Another question. Have you tested these samples using Materials International Space Systems Experiment, the MISSE platforms?
Yes, that material is actually included in one of those MISSE missions. I'm not too familiar with it, but I do know that it has previously been out there. I believe we haven't received the results from that yet, though.
Okay. Here's a question about whether you've investigated white kapton from DuPont.
I don't believe we have investigated that yet, no.
Okay. All right. And let's see, here's another straightforward question. Why the greater transient variations in the AZ93?
So the graph itself, the output for thermal desktop wasn't kind of very frequent, and so you kind of see a lot of the spikes, but it seems to be that the white paint samples kind of respond more or heat up faster than the solar white or yttrium oxide sample. So some of the spikes are a little bit misleading due to the output of the thermal desktop. But yeah, my guess is that it's due to the coating and difference in optical properties. I believe the AZ93 absorbs about 15% of the solar radiation, whereas the yttrium oxide absorbs about 1%. So I would definitely attribute it to the optical properties.
Okay, let's see. We do have another question that popped up. What are the next steps required before this coating will be ready for broader implementation on spacecraft?
So there's a lot of interest going around in this thermal control coating, and the main idea behind this CubeSat is to kind of build that confidence so that we can kind of take the next step. It'll increase the technology readiness level from 2 to 3 to like maybe a 4 or 5. And so we're kind of slowly trying to get that confidence built up to where we can get to the next level. But this is definitely, progress in the right direction, getting this material out in space and getting a real reading on what sort of temperatures we get in orbit.